you can do exactly what I told you with a simpler thing. Let me take another example. Let's say I want to implement a plus bc whole bar. Okay. So first step, invert function. Invert y implies y bar is a plus bc. Okay. 2. Implement, pull down network. Okay. So we'll first do this step. I have a plus bc. How do I implement this? A in parallel with b and c. A in parallel with b and c. Okay. This is my output. Now, to get the pull-up network, just construct the dual of this network. Make every series parallel, every parallel series. Right? So I have B and C in series. Right? I need to make that in parallel and then make it in series with A. Okay? That's the way you construct the dual of the network. So I will simply say A B and C. Okay? Clear? So if you look at the function on the pull down network, YPDN is what? A in A plus BC whole bar, because it's going down to 0. The Y pull up network function is what? A bar plus A bar into B bar plus C bar. Right? Note that these two are Boolean equivalents. De Morgan's laws, I can take the complement inside, make and or and these two are the same. Okay, this is your check. Eventually, both of these things should be the same. Yes. Absolutely. So there are certain cases where these things are equivalent, where logically it's okay to put one on top, one below. I will tell you how to resolve this once we get into the timing, because timing wise they are not the same, delay wise. Okay. Any other question on implementing this logic? So then let's do one more example which is slightly more complex. A plus B into C plus D whole bar. Can you implement this? Is this the pull down network? Yeah. What about the pull up? Again, I have to have A now in series with the whole thing, right? In series with B has to now be in parallel with C and D in series. B C and D. Okay, clear? So with this systematic method you can construct any arbitrary Boolean function. Okay, whether it will be efficient or not, we have to see later. But you can construct any static CMOS logic in this manner. Okay. So now let's move on to the question of sizing. Okay. So we said that when we had a CMOS inverter, we said that the W, right? For example, this would be 4 lambda by 2 lambda, W by L. This would be 8 lambda by 2 lambda, W by L. Okay, A and Y. And why did we have this twice? So that the pull up delay and pull down delay are same, right? The delay is symmetric. That's the reason we made WP equals 2WN. Okay. Now going forward, since the length is always going to be 2 lambda, right, and the inverter's width, right, will also be fixed by the technology parameters and so on. And in the sense, depending on the technology, the designer will say, okay, my minimum width that I can use for the inverter is, let's say, 4 lambda or 8 lambda or whatever. We are going to abstract this whole thing out and simply call it 1. And this will therefore become 2. So from now onwards, I will just write a CMOS inverter like this. I will say 1 and 2. You must interpret it as the width alone is doubled for the PMOS transistor. Okay? And this is what I will also call a reference CMOS inverter. This is my reference CMOS inverter because all the gates that I build from here on will be sized with reference to this inverter. Okay. So let's say now I have a NAND 2 gate. Y equal to AB bar. Okay. So what I'm going to do is I'm going to put 2 NMOS transistors in series. A, B. What will be the pull-up network? 2 PMOS transistors in parallel. VDD, A and B, and this is my output Y. So with reference to this CMOS inverter, I now need to size these transistors in my NAND gate. Okay, so for example, one possible thing to do is do the same thing. I will say 1, 1, 2, 2. Right? We understand why we did 1, 2, so that the pull up and pull down delay is symmetric. So I can do 1, 1 and 2, 2. Right? Now let us examine what happens to the worst case pull up or pull down resistance. Okay, that is the primary criterion that we are going to pick in order to size these gates. So we will look at worst case pull up or pull down Okay. Now we did this earlier. Okay. So, and when I say resistance for what? It's the resistance for delay. Let us assume that a capacitor here is being discharged. It has VDD initially, and that is now being discharged through this pull down stack, right? I want to look at the worst case resistance that will be offered by that stack, right? And ensure some constraint on that. Okay, so first let us look at when we had a single transistor with size 1, unit width 1, right? As defined here, by the way. This 1 is as defined here, right? Then the resistance we calculated for this NMOS was some R. I'm going to drop that R equivalent N or whatever. I'm going to call it R. Okay. Now if an unit NMOS has resistance R, what will be the resistance of an NMOS with twice the width? R by 2, exactly. So why is that? Let's look at that. R was basically 3 VDD by 4 ID SAT. Correct? This is what the expression we got. And now if my width goes up by 2 or by a factor alpha, right, then the resistance is going to be R alpha is 3 VDD by 4 into alpha times ID SAT, because ID SAT is proportional to W. If I increase my W, I have more current, linearly more current, and therefore 1 by alpha times the resistance. Therefore, this will be R by alpha. So this is R by alpha, right? So what do I have on this NAND gate where I have assigned a unit width to both NMOS transistors? What is the net pull down resistance? It is 2R, right? So if you look at the pull down network's resistance, it is basically R and R. So if I compare this to my reference inverter's pull down resistance, it is twice that, right? Because this guy has a pull down resistance of R. My design is to, by design, I want to make sure that the worst case pull down resistance on that pull down network is exactly equal to the pull down resistance of my reference CMOS inverter. Okay, therefore I have to make this one as some alpha, and we'll calculate what alpha is. I'm going to make it alpha, right? And the net resistance is now going to be what? R by alpha. This will be 2R by alpha. But by design, I want this to be how much? R. Therefore, alpha has to be 2. Right? And therefore, this will be 2. Is that clear? Yeah. So, the point is that ideally, I would have liked to size my transistors to the unit width because I want to save on area, right? Why would I make it any bigger, right? I want that to be. Of course, PMOS, because mobility is half, I have to double the width. That we know. Now, if I make it unit width, then the net pull down resistance for this NAND gate is R plus R, which is 2R. So, by design, I want the worst case pull down resistance to be only as much as that offered by a reference CMOS inverter. The reference CMOS inverter is this guy. How much does he offer? He offers R. I want the net worst case pull down resistance. Remember, this is a very important thing. The worst case pull down resistance should be R. It can be better than that. There's no problem. In certain combinations, it may even be better. But the worst case should be R. And therefore, I have no choice but to double the size of my NAND 2 NMOS transistors in order to match this constraint. Right? Therefore, for a NAND gate, NMOS transistors both will have a size 2 for a NAND 2. What about the PMOS? What is the worst case pull up resistance. No. So what is the worst case constraint? Is it one of the transistors pulling up or both? It is only one transistor pulling up, because if both resistances are in parallel, it will fall by 2 anyway. That's not the worst case. So the worst case is one of the transistors pulling up, and therefore I can keep that size to 2, because that is the same as the reference CMOS inverter, where I have one PMOS pulling up with a size 2. Here again the worst case is just one PMOS, and therefore I can make the both PMOS's size 2. Okay, so we'll stop here. We will continue tomorrow with more examples of the NAND 3 and NOR 3 and so on, right, where all of this will become more clear. Thank you.